Welcome to the third video of stoichiometry. We are going to introduce what percent yield is in this video. What you have learned in video 2 and video 1 will apply still here, but you're going to have an extra step at the end so that you can figure out what the percent yield will be for the reaction. As you can see on your screen, there's an equation for percent yield, and that is going to be the actual value divided by the theoretical value multiplied by 100 so that you can get a percent as your answer. So let's go ahead and dive into two different example problems. Again, before I show either one of those, you need to have a balanced chemical reaction before you even start the problem. So let's go ahead and see how that is. Our first example problem states, what is the percent yield if 13.1 grams of calcium oxide is actually produced when 24.8 grams of calcium carbonate is heated, and the reaction is given to you. Before you go ahead and start anything here, we need to make sure that we have a balanced chemical equation. We have the same amount of calciums on each side, we have the same amount of carbons on each side, and if you add up the oxygens on your product side, you'll see that the oxygens are the same amount on each side. So we have a balanced chemical equation to start out with. If we do not, you need to go ahead and balance it before you move on to the next step. When we go ahead and read through what the problem is, there's a few things that you should probably be writing down. You can now see on your screen that I wrote down the 24.8 grams underneath the calcium carbonate as it was stated that we have in the problem. The other number that's now given is the 13.1 grams of calcium oxide. And the wording sometimes throws people off, but you need to figure out which of the two numbers is the actual number that you need to be putting into your percent yield problem. This is the part that's new here. So the 13.1 grams actual number for calcium oxide, I went ahead and listed right underneath there. The theoretical number that I have listed here, we don't know. And in video 2, this is what we were calculating. Every single time you start with a reactant and you're trying to go from grams to moles to moles, and moles back to grams, going from reactant to product here, that is going to be your theoretical number. So what that means is, in an ideal setting, perfect world, everything goes 100% the way it's supposed to in your chemistry lab, the theoretical number is what we would be predicting we should get. Now in real life, theoretical numbers are normally a little bit high because something is bound to go a little bit off or really off depending on what the reaction is. And so the actual number is going to be of importance here because this tells you how much you actually get versus how much you should have gotten, and you can get a percentage of what that reaction is going to go ahead to completion. So if you have a really high percent yield, that's great. But if you have a really low yield, you might want to tweak something in the lab, and depending on how things go, you might not even go ahead and do the reaction then. So let's go ahead and work through that grams to grams, so grams of reactant to grams of product, just like we did in our prior video, and then we'll go ahead and apply the percent yield. You can now see the dimensional analysis for our problem. We start with the 24.8 grams of calcium carbonate in our first square. We want to convert this to moles of calcium carbonate first, and so we have the molecular weight in this step. This is always when you want to calculate for 1 mole of whatever your element or your compound is, and so that's 100.09 for calcium carbonate. This mole to mole step occurs, and we have 1 to 1 because our coefficients between the two of these are 1 to 1. This is the step that converts us from a reactant to a product. In our last step, we want to go from moles of our product to grams of our product, so we can go ahead and get our theoretical number, which you see down here. So we want to go ahead and do calcium and oxygen, get the masses of that, and that would end up being 56.08 grams. If we multiply this across, multiply all the numbers on the top, multiply all the numbers on the bottom, and then divide at the end, with significant figures you should be getting 13.9 grams of CaO, or calcium oxide. This is our theoretical number when we plug in to percent yield. When we calculate percent yield, as you can see at the bottom of your screen, you want to do your actual number, which is 13.1, as we've written up here and talked about. Our theoretical number is going to go underneath this, and we want to multiply that by 100 so we get a percentage, not a decimal point. And so keeping with 3 sig figs, since we had 3 sig figs from the get-go, we have a 94.2% yield for this reaction. For our next example, we're going to go from the very start all the way through. And so you'll realize that we are not going to give you a balanced chemical equation, nor are we even going to start you with the bare bones. You're going to start with the wording of the reaction, make your own chemical reaction with all the compounds formulas, and then go ahead and balance it before you do any of the stoichiometry. So let's go ahead and see what our problem states. Chlorine reacts with potassium bromide, yielding potassium chloride and bromine. What is the percent yield if 0.500 grams of bromine is actually produced when 5.00 grams of potassium bromide reacts? We need to go ahead and take the first sentence and put it into a chemical reaction and get that balanced first before we do anything else. So reread the first sentence if you need to and change that into the compounds. So now that we're looking at our balanced chemical reaction, there's a couple things you need to remember. The first thing is chlorine and bromine by themselves should be diatomic. That's why we have that subscript there. We also have potassium bromide and potassium chloride. We need to do our charge balancing. Once all of that is completed, then you can go ahead and balance this reaction, which is where the 2 coefficients of 2 in front of potassium bromide and 2 in front of calcium chloride should be showing up because of you getting that balanced chemical reaction. So now that we have that balanced chemical reaction, we need to go ahead and start our stoichiometry. So the first sentence is all about getting our chemical reaction, and then we go ahead and balance it. But the second part is the actual question for our stoichiometry. So let's reread that and make sure we have everything in the places that we need. So it says, what is the percent yield if 0.500 grams of bromine is actually produced? So I'm going to pause there. That is what this number is, and Br2 is our bromine. Let's continue back to our question. When 5.00 grams of potassium bromide reacts, which is right here. Okay, so we wrote down the 2 numbers, the 5.00 grams and the 0.500 grams. This is our actual number, and this number for our reactant is what we're going to use to figure out our theoretical number. Notice that you need the actual and the theoretical number of the same product, otherwise you are not able to do a percent yield calculation. So that's why you have both of these listed together. Now we need to go ahead and set up our stoichiometry to change this amount of grams to grams of bromine. So now on your screen is the dimensional analysis. As always, we start with what's given in our first box. The second box, or the second part that's divided there, is our molecular weight of potassium bromide. Here's our mole to mole conversion. In this example, you have different numbers than 1 to 1. These numbers again come from our coefficients above. So we have 2 moles of potassium bromide because there's a 2 right here. We have 1 mole of bromine because there's a 1 technically right here. It's just not written as we're used to. At the very end here, this is another molecular weight, but this is our molecular weight of Br2, or our bromine. Whenever you have the subscript, remember that you do have to go ahead and multiply whatever this element is by 2. Never work in the coefficients into your molecular weights, as it's always per 1 mole. So you can see that here, and you can see that here. The only time you should have anything other than 1 mole is in this step here, the mole to mole conversion. So I'm going to uncover what our answer should be for this. Remember, multiply across and divide the top by the bottom at the end. And then we're going to also have our percent yield on the screen as well. Okay, with significant figures, you should have gotten, with our significant figures, we should have received or calculated 3.36 grams of bromine. So we see that over to the bottom left. Plugging in our actual number over our theoretical number, multiplied by 100, or just plugging into the percent yield equation, you should have a percent yield of 14.9%. When you're doing chemistry in the, real world outside of a high school type setting, doing research or even for a job, the percent yield is very different from the last example here. 14.9 respectively to our first example is much lower. And just to remind you, our last percent yield was 94.2. So things like this are what chemists look at to see, do you pursue the problem? Do you need to try to increase the percent yield because something's going on in the lab that might not be optimal, things of that nature. So this is actually used quite a bit for everyday things that you might be using right now. At this point in time, percent yield should be very apparent. You just do actual over theoretical times 100. The only new thing between video 3 for stoichiometry and video 2 for stoichiometry is introducing that part, having an actual number and doing the percent yield equation. If you need to, go back to the beginning, look at the equation again, get it written down in your notes or take a screenshot of it and practice with some more problems.